Otherwise I'll forget. Okay. So let's think about rewriting h of x. We can see what our quotient is. Will this let me resize? I want to shrink it. I want to shrink it. There it is. Okay. So let's think about rewriting h of x. And to reinforce that, I'm going to copy h of x down here. So h of x can be written as negative 2x minus 4 plus the 6x minus 43 is our remainder. So we take 6x minus 43 and put it over the denominator there, yeah. Okay, so we've already thought about taking the limit of h of x using end behavior model, but let's think about, again, taking the limit as x approaches just infinity, although you could do either direction, of h of x. So that's thinking about taking the limit as x approaches infinity. And if I think of h of x being written in this other form, maybe you see where I'm going with this. But by the associative property of addition, I could group these terms, and then I have the fraction here. And applying the sum property for limits, if I thought about having the limit as x approaches infinity of negative 2x minus 4 plus the limit as x approaches infinity of 6x minus 43 over negative 2x squared plus 5x minus 9. So then you guys, as x approaches infinity, what's negative 2x minus 4 approaching? Negative infinity, right? Like this would be going to negative infinity. What would this be going to? 6x minus 43 over negative 2x squared plus 5x minus 9. You could think EBM, if it would help, like what would the end behavior model here be? So it would approach 0. Do we see that? Do we see it? See it? End behavior model? Would approach 0. So we already knew that this limit was going to be equal to negative infinity. But now you guys can kind of see when the equation for h of x is written in this form, like why we say that negative 2x minus 4 is the equation that guides the function's end behavior. Because the function is approaching negative infinity and positive infinity, but in the same way as y equals to negative 2x minus 4. Like if we were to look at the graph, and before I switch over to Desmos, I can conclude that there is a slant asymptote at y equals to negative 2x minus 4. Which you guys knew from like pre-calc identifying a slant asymptote. You just did the polynomial long division and you're like, hey, the quotient ends up being a slant asymptote. My point in showing you this, like rewriting h of x in this form and thinking about taking the limit, is to prove to you why that is the equation that guides the behavior. That specific equation is the equation that guides the behavior of the graph. So if I go over to Desmos and I type in the original, so what is it, 4x cubed minus 2x squared plus 4x minus 7 divided by negative 2x, squared plus 5x minus 9. And you're like, okay, like kind of locally, I see a little curve. And then if we zoom out, we're like, if we type in what our end behavior model was, we're like, oh yeah, those have similar end behavior. Doesn't it kind of look like they're almost like parallel lines though, whenever you zoom out? And then if we put y equals to negative 2x minus 4, our slant asymptote, okay, so up close you're like, oh, those look like similar end behavior, but as you zoom out, you're like, hey, it looks like those are two lines that are merging together, right? So we use the slant asymptote to describe how the function is getting to where it's going as x gets infinitely large or infinitely small. It gives us kind of a clearer picture than what our end behavior model does. End behavior model, I always think of it as being like kind of like a blurry picture. Good? Okay. Sometimes the degrees of the numerator and the denominator are not as explicit. This often occurs when either the numerator or denominator are under a radical. For these types of problems, we can use a similar analysis. So functions like these may have 2 or 1 end behavior asymptotes. It's important to analyze the simplified ratio of the leading terms to get the value of the limit. And then based upon the type of infinity we're approaching, determine the sign SIGN of the limit. That's a lot of words, and I think it'll make more sense, and we can kind of reference back here after we've done an example together. Okay, so something like this. We're trying to talk end behavior, just like we were with those rational functions before, but this is not a rational function. Remember, by definition, a rational function is a ratio of 2
functions.
What type?
Real functions.
Look at the previous examples. In the numerator and denominator, what types of functions? Polynomial functions. A rational function, by definition, is a ratio of 2 polynomial functions. This is not a polynomial function, right? Like this would be a radical function. If anything, a radical function composed with a polynomial function. So we want to determine the limit as x approaches infinity of f of x, as well as the limit as x approaches negative infinity of f of x. We are going to use the same sort of strategy of thinking about end behavior models. So as x gets infinitely large or infinitely small, in the numerator, which term will dominate? 4x. What about the denominator? The square root of 9x squared, right? So this ratio is going to be our end behavior model. Before we simplify, don't go ahead of me right now. You haven't done this before. Before we simplify, let's think about what the signs of the numerator and denominator could be. So as x approaches infinity, 4x would be positive, right? As x approaches negative infinity, 4x would be negative. So the numerator, depending on which infinity we're taking the limit for x approaching, can be positive or negative. However, the denominator with this square root for either infinity would be positive. It is implicitly positive. Like the denominator will only give positive outputs if you're thinking about substituting in numbers, whether they're getting really large or really, really small. Okay, so now if we think about simplifying here, what does the denominator simplify to? 3x. Okay, the x's would cancel, leaving us with 4/3. The thing is, 4/3 could be positive or negative depending on which infinity we're taking the limit x approaching. I said that in a weird way. Well, our limit could either be positive 4/3 or negative 4/3 depending on which infinity x is approaching. So then we think, okay, as x approaches positive infinity, the numerator, I think it's helpful to go back to your original EBM. The numerator would be positive. The denominator would be positive. Positive divided by a positive would be a positive. So this limit would be positive 4/3, which indicates by definition that there's a horizontal asymptote for f of x that describes its end behavior as x approaches infinity. I started spelling horizontal again. Asymptote. At y equals to positive 4/3. But then referencing our end behavior model as x approaches negative infinity, the numerator would be negative divided by a positive is a negative. So this limit would end up being equal to negative 4/3, indicating that as x approaches negative infinity, f of x has a horizontal asymptote at y equals to negative 4/3. And I'm not going to graph all of these, but let's just peek at this one. So if I type in y equals 4x minus 2 divided by, oops, that's not what I want, divided by the square root of 9x squared plus 8x plus 1. Okay, so you can kind of see it looks like there's a vertical asymptote in there, but we're talking end behavior right now since we're thinking limits at infinity. And notice when I put in y equals to 4/3, bam, y equals to negative 4/3, bam. Okay, so we have our two different end behavior asymptotes there. Questions? Okay, I want you to go ahead and determine end behavior, and if there's any end behavior equations for the next two, let's do U3. Let's do U2 and then U2. But you just turn and talk, right? So go ahead and determine, first of all, the limits as x approaches positive and negative infinity for each of these functions. And then based on those limits, determine if there's an end behavior equation that we can come up with to describe the end behavior of either g of x or k of x. Talk to your group or partner.
mean, x to the sixth, yeah, because it's x times x, 6x is 1x to x squared x. Limit. We need to radical.
But if you put more money,
The limit is x is approaching infinity is oh, we have to do C also? Oh, it's
Jack, your partner is Sophia.
but Ian's like,
Ian, give Jack space.
yeah, give me personal space. Yeah.
is the person not really positive?
No. Because it's -5 over. So x over 11. Right, 'cause
Are you guys already done?
yeah.
They're too fast.
It matters, 'cause isn't it 0 for both of them? What? What?
It's always negative.
Yes. Or it doesn't matter if it's negative. What? What? Just
It's Lucha.
Lucha.
Oops.
What did you put from the top?
I put like,
Like 50-50? I
Yeah.
put 50.
I did that because you said the conversation with the Guatemalan lady
Yeah.
from,
Is it? Very cute.
What do you mean?
like,
On the
'cause you
floor.
fill out the form, right?
Yeah, well,
It says 50% like 3,
Like,
and then
yeah,
50%
structure. I don't know.
No, Trevor did 50.
Okay, it sounds like we are ready to check in.
Yes.
Okay. So, where'd my button go? There we go. Okay, so for g of x and behavior model, you're like negative 2x cubed over the square root of root 11 times x to the 6th. That numerator could be positive or negative as x approaches positive or negative infinity. The denominator, however, would be positive. When simplifying, the denominator can be turned into root 11 times x cubed, so those x cubes could cancel. But don't just say that both the limits are negative 2 over root 11. Remember, you have to do the analysis to determine what the sign would be. So thinking about as x approaches infinity, if you're cubing really large numbers, they're going to be positive large numbers. But then when you multiply those positive large numbers times negative 2, won't they be really small negative numbers? So negative divided by a positive would be a negative, indicating that there would be a horizontal asymptote at y equals to negative 2 over root 11. Do we agree? Now, if you had rationalized the denominator, that's fine. For your response, I wouldn't waste your time trying to simplify or do something like that. Where it would be important is if you had some sort of multiple choice question where you're trying to get your answer to match one of the options that's there. Like if negative 2 over root 11 wasn't there, but let's say negative 2 root 11 over 11 was. And then you would want to be able to do that manipulation, okay? And then as x approaches negative infinity, well, when you cube a negative number, you get a negative number. And then when you multiply by a negative number, you would get a positive number. So a positive divided by a positive would be a positive. So positive 2 over root 11, meaning there's a horizontal asymptote as x approaches negative infinity at that horizontal line. Questions? Okie dokie, next one. I started by identifying end behavior model. I was like, I'm going to think of signs as x approaches positive or negative infinity. But then I was like, oh wait. Our end behavior model ends up being a version of 1 over x that's been transformed, right? 1 over x being reflected, vertically stretched by 5, horizontally compressed by a factor of root 11. But that doesn't change the end behavior of 1 over x, right? Like if you think about applying all those transformations, like you can still think 1 over x, or you could think from the perspective of, okay, if I'm plugging in larger and larger values for x, what would be happening to this? Or plugging in smaller and smaller values for x, what would be happening to this? It would be approaching 0, exactly. Or even a limit, like if you thought about like direct substitution of infinity, which for the recording I'm putting in quotations because direct substitution of infinity is kind of a weird thing to think about. But then you'd end up with a constant over infinity, which is 0. So k of x just has a horizontal asymptote that describes the end behavior in both directions. Good? Questions? Sweet. We are done with 3.5. And we are, that's not the right day. We are switching over to,
Wait, so were we behind?
dun, 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 dun. Nope, I had to do this with everybody.
Oh.
We are switching over to section 2.1. I was telling the classes yesterday, I need to get like a new intro for this lesson. I think everyone is kind of tired. Tired of hearing about COVID-19 cases, but it's also not so much relevant because like how old were you guys in spring of like March 2020?
I feel like I was
Sixth grader?
6th grader? So whether you were watching, Jack, you were probably watching the news then, right? You remember graphs like this.
I watched CNN. Oh, well, I was.
Dude, Carl.
Anyways, I need to get
Carl
like new
kind of gave
material.
us no real.
Those will work.
He told us a bunch of like small stuff.
So this graph, I should have cited my source. So this graph is from our world in data, so it's legit data. So let's talk about what's in this graph, like what's represented. So the horizontal axis we can think of as being the x-axis, or if you want to call it the t-axis, you could. Represents the days after March 1st, 2020. So that means whenever x is equal to 0, this point right here represents March 1st, 2020. Right? That's whenever x is equal to 0. And then the vertical axis, which you can think of as being the y-axis, or calling it something else, represents the daily new confirmed COVID-19 cases. So like the different values that are on here is not representing like the cumulative number of COVID-19 cases, it's the number of new cases that were found like that day, like the number of new people that tested positive that day. So as time is passing and we're getting deeper into March, what does it look like COVID-19 cases. They're going up, right? They're increasing. Okay. They are increasing. What type of curve does it look like this data kind of makes?
So.
Exponential. So it looks like the number of COVID-19 cases, of new COVID-19 cases, is increasing exponentially, right? Like this looks like exponential growth. So again, not like cumulative, not the total number of cases at any one time, but it's the number of new cases, like the number of people that would have tested positive on a particular day. So let's say that from reading this graph, it appears that on March 1st, 2020, there were approximately 2,500 new COVID-19 cases. So that means that we could label this point right here as 0, 2,500. On March 11th, 2020, there were approximately 7,500 new COVID-19 cases worldwide. What X value would correspond to March 11th, 2020? 10. Do we see that? So this point right here would be 10, 7,500. Who has a cat? Perfect! Rose, Sophia, you guys are going to work together for the next question. Who has a dog? Perfect. You two. Who has no pets? No pets?
Ian can work with.
Okay, how about you three will be together? So then you two and then you three. Perfect. Okay. So with your grouping or your pairing, you're going to answer this question. What can we say the average increase in number of new COVID-19 cases were per day? That's worded weird, isn't it? What can we say the average increase in number of new COVID-19 cases were per day was from March 1st, 2020 to March 11th, 2020. So the average rate of change over this time period. What is the increase in the number of new COVID-19 cases? Hey, do I just not need were? Is were just an extra, like, do I not need that?
I think so.
Just get rid of that. Okay, so with your partner or your group, you guys can talk. And then you can face Malika and Gabby. You guys can chit chat about this. And then go ahead and also talk about what's the graphical representation of this number.
Yeah. I'm just doing 10 minus 0. That's 5,000.
Okay, sounds good. Okay. So what do we do now?
Plugging it into a function.
Why not?
It's not pleasant.
It's my new way of shushing people. So if like Jack and Ian won't stop talking, then shh.
That's crazy.
Oh god. Why does that exist in the first place?
Fabio made it for the beginning of the mall to make basketball dinner. We just have to like face that way.
Maybe just lead it up.
You're gonna terrorize the junior high with that.
It's not. It's like school choice.
Can I look? Are they legit?
It's just they're like it looks like some just random people, sophomores, juniors, seniors. Okay. Do we have an answer, you guys? Okay. So, what is the average increase in number of new COVID-19 cases per day? What do we get? 500. Can you tell me how you got that number?
Yeah, we did 7,500 minus 2,500 on top over 10 minus 0.
So you did 7,500 minus 2,500, which would give you the difference in the number of cases, right, per day from March 11th to March 1st. And then over the number of days that have passed, right? So from the last day on that interval to the minus the first day on that interval. Okay. And then 7,500 minus 2,500 would be 5,000 over 10. If you're thinking units, this would be number new cases over number of days. So you could say there would be 5,000 new cases every 10 days. Or you could simplify that to be 500, which you can think of as 500 over 1, right? 500 new COVID, make sure you put units, 19 cases per day. What is that? What did you do in order to calculate that? What did you use? The slope. Isn't that the slope of the line that passes through these 2 points? So this is the slope of the line that passes through 0, 2,500 and 10, 7,500. Like that's the calculation that we did in order to calculate that average rate of change. So that's the slope. 500 is the slope of that line. Do you know what that line's called? That intersects the curve at 2 points?
Tangent.
It's not tangent. Tangent intersects at 1 point. It's a secant line. So this is the slope. 500 new COVID-19 cases per day is the slope of the secant line on the interval 0 to 10. Now, we're going to focus in. So March, let me use another color here. March 5th would correspond to when X is equal to, what would X be equal to for March 5th, 2020? if March 1st is x equal to 0, are we awake? Are you going to make it? Are you really tired? Did you get enough sleep last night? No. Okay. What value of x corresponds to March 5th, 2020?
4.
4.
Shoot.
Don't just throw out numbers. Okay? So this would be March 5th. Right? March 6th would be this point right here. 2020 for both of them. Do those points lie above or below the secant line? Below. Yeah, my secant line's kind of funky, but they look like they lie below. So, if we were to use the equation of the secant line to make predictions of what the number of new COVID-19 cases was on March 5th or March 6th, do we think that our secant line would give us approximations that are overestimates or underestimates? Overestimates, because the secant line lies above the data. On that interval. Okay, so like if we were coming up with the equation of the secant line, we've already come up with the slope, right? And this is on the interval from 0 to 10. So the slope was 500. What's the y-intercept? Read the graph, guys. What's the y-intercept? Yeah, B would be 2,500. We can see what the y-intercept is in this case. So B would be 2,500. Okay, so if we were to use this equation to try and predict the number of new COVID-19 cases on like March 5th, you could either use this equation or you could just kind of count up by 500. You'd get the same value. So like if we did y equals to 500, times 4 plus 2,500, we get 4,500 new cases, COVID-19 cases. Or for March 6th, which would be x equals to 5, or you could just add another 500. Right, we get 5,000 new COVID-19 cases. I think conceptually you guys can understand you don't have the proper justification yet to like using calculus, but I think conceptually you could see that both of those values, both of those approximations of the new number of new COVID-19 cases for each day are overestimates. Of what the actual number of new COVID-19 cases was per day, because the data points are below the secant line on the interval from 0 to 10. Okay, we're almost to where I want to stop. But we're doing like really, you guys are my third time, so we just like always go through things so much faster. I think that's why. I think that's part of it. Do you need to go get fresh air, get some water, do some jumping jacks?
I'm like alive, I promise.
Like stand up, stretch, touch your toes, I don't know.
I've been sitting up, I'm like waiting outside.
What time did you go to bed last night?
12:30. And I woke up at 6 to get ready for the day, and I already want to retake.
Sheesh. I got like 8 hours of sleep and I'm about to
I
crash.
slept at 10.
I know Ian got at least 13 hours of sleep. When did you go to sleep, Ian?
Like 10:30.
That's late.
I was
right?
staying for late.
That's
And
a
then
late
I
night.
called
for
my
me.
baby cousin.
Oh, at 10:30?
Yeah, because.
Who's a baby? You call, oh, okay.
And
Okay.
I was at 12.
Okay. So you just calculated an average rate of change over an interval. What's the difference between talking about the rate of change in number of new cases over an interval of time versus on a particular day? I kind of just give the answer to part of it.
Over a number is like average.
You mean over an interval of time?
That's
Would be the average rate of change, yeah. So out over an interval of time, we'd be talking about average rate of change. Versus on a particular day, we are talking about and it depends on what the unit of time is in the graph or in the for the independent variable or in the table. Whether it's like talking about on a particular day, a particular second, a particular hour. In that case, when you're calculating rate of change on a particular day, we would be talking about the
Fixed amount. A number.
we would be talking about the instantaneous rate of change. I know. Jay said, yeah, didn't Mr. Hamilton refer to average rate of change, AROC? Abbreviate AROC? AROC? Average rate of change is when we're talking about over an interval of time versus instantaneous rate of change would be talking about at a particular moment in time. And then this next part is where we're going to finish off. So in general, average rate of change of a function over an interval can be calculated by finding the slope of this secant line, which is what you just did, right? That passes through the 2 points that represent the ends of the interval. So just in general, if we think about having a function, I'm just going to draw a curve that's in Q1 for simplicity. I'll draw something similar to what we just had. Woo, let's call that the function f. And then let's say that we are calculating the average rate of change of the function over the interval from x sub 1 to x sub 2. So one endpoint to the other, first x value to the second x value. You could use a and b. I'm just going with the notation that I have here for slope of a secant line, meaning this point can be described as x sub 1 comma y sub 1, or with function notation, if we're calling this the function f, could be x sub 1 comma f of x sub 1. And then this point right here is x sub 2 comma y sub 2, and with function notation can be written as x sub 2 comma f of x sub 2. The line that passes through those 2 points is referred to as a secant line. Okay, so on this interval for x sub 1 to x sub 2, and the value of the slope would be the average rate of change for the function f over the interval from x sub 1 to x sub 2. So if we were to rewrite this with the function notation, it would look like this. F of x sub 2 minus f of x sub 1 over x sub 2 minus x sub 1. And here is where we will end, and we will pick up next time. You do not have homework on 2.1 yet. Your only homework is on 3.5. We have so much time.
Math time?
This is where I finished for the other classes. Should we keep going?
No.
No, because then we'll just be like uber ahead, huh?
Yeah.
You don't wanna
Okay.
spoil